20th International Physics Olympiad. Year 1989. IPHO. I offer private tutoring for preparation for physics Olympiads. I currently have openings. Write to me if you are interested. There is a discount for group lessons. My email is fred1996@hotmail.com. Problem 2. Rotating masses. The solution to this problem can be found at the link in the description under this video. Three noncollinear points P1, P2, and P3, with known masses M1, M2, and M3, interact with one another through their mutual gravitational forces only. They are isolated in free space and do not interact with any other bodies. Let sigma denote the axis going through the center of mass of the three masses, and perpendicular to the triangle P1P to P3. What conditions should the angular velocities omega of the system, around the axis sigma, and the distances P1 P2 equals a 1 2, P to P3 equals a 2 3, P1 P3 equals a 1 3, fulfill to allow the shape and size of the triangle P1 P to P3 unchanged during the motion of the system? That is, under what conditions does the system rotate around the axis sigma as a rigid body? Solution to second problem. As the system is isolated, its total energy, that is the sum of the kinetic and potential energies, is conserved. The total potential energy of the points P1, P2, and P3 with the masses M1, M2 and M3 in the inertial system, that is when there are no inertial forces, is equal to the sum of the gravitational potential energies of all the pairs of points, P1, P2, P2, P3, and P1, P3. It depends only on the distances, a 1 2, a 2 3 and a 1 3, which are constant in time. Thus, the total potential energy of the system is constant. As a consequence, the kinetic energy of the system is constant too. The moment of inertia of the system with respect to the axis sigma depends only on the distances from the points P1, P2, and P3 to the axis sigma, which, for fixed, a 1 2, a 2 3 and a 1 3 do not depend on time. This means that the moment of inertia I is constant. Therefore, the angular velocity of the system omega must also be constant. Condition 1. This is the first condition we had to find. The other conditions will be determined by using three methods described below. However, prior to performing calculations, it is desirable to specify a convenient coordinate system in which the calculations are expected to be simple. Let the positions of the points P1, P2, and P3 with the masses M1, M2 and M3 be given by the vectors R1, R2, and R3. For simplicity, we assume that the origin of the coordinate system is localized at the center of mass of the points P1, P2, and P3 with the masses M1, M2 and M3, and that all the vectors R1, R2, and R3 are in the same coordinate plane, that is in the plane x, y. Then the axis sigma is the axis z. In this coordinate system, according to the definition of the center of mass, we have equation 2. Now we will find the second condition by using several methods. First method. Consider the point P1 with the mass M1. The points P2 and P3 act on it with the forces in the expressions 3 and 4, where G denotes the gravitational constant. In the inertial frame, the sum of these forces is the centripetal force Fr1 equal negative m1 omega square r1, which causes the movement of the point P1 along a circle with the angular velocity omega. The moment of this force with respect to the axis sigma is equal to 0. Thus, we have expression 5. In the non-inertial frame, rotating around the axis sigma with the angular velocity omega, the sum of the forces, 3, 4, and the centrifugal force F prime R1 equal m1 omega square R1 should be equal to 0. Expression 6. The moment of this sum with respect to any axis equals to 0. The conditions 5 and 6 are equivalent. They give the same vector equality. Expressions 7 prime and 7 prime prime. From the formula 2, we get expression 8. Using this relation, we write the formula 7 in the following form. That is, the vectors R1 and R3 are noncollinear. Therefore, the coefficients in the last formula must be equal to 0. The first equality leads to, and hence, A13 equal A12. Let they be equal to A. Then the second equality gives equation 9, where big M equal M1 plus M2 plus M3. Expression 10 denotes the total mass of the system. In the same way, for the points P2 and P3, one gets the relations A and B. Summarizing, the system can rotate as a rigid body if all the distances between the masses are equal. Expression 11. The angular velocity omega is constant and the relation 9 holds. This was the solution to the problem in the first way. Second method. At the beginning we find the moment of inertia I of the system with respect to the axis sigma. Using the relation 2, we can write expression 12. Of course, vector Ri square equal R square for I equal 1, 2, 3. The quantities 2 Rij for all Rij can be determined from the following obvious relation 13. We get equation 14. With help of this relation, after simple transformations, we obtain expression 15. The moment of inertia I of the system with respect to the axis sigma, according to the definition of this quantity, is equal to 16. The last two formulae lead to the expression 17, where m, the total mass of the system, is defined by the formula 10. In the non-inertial frame, rotating around the axis sigma with the angular velocity omega, the total potential energy V total is the sum of the gravitational potential energies 18 of all the masses and the potential energies 19 of the masses Mi in the field of the centrifugal force. Expression 20. That is V total equal expression 21. A mechanical system is in equilibrium if its total potential energy has an extremum. In our case the total potential energy V total is a sum of 3 terms. Each of them is proportional to Fa equal 22. The extrema of this function can be found by taking its derivative with respect to A, and requiring this derivative to be 0. We get equation 23. It leads to 24. We see that all the terms in V total have extrema at the same values of A, Ij equal A. In addition, the values of A and omega should obey the relation 24. It is easy to show that it is a minimum, because the second derivative is positive. Expression 25. Thus, the quantity V total has a minimum at A, Ij equal A. This means that our three masses can remain in fixed distances only if these distances are equal to each other and relation between A and omega are in expressions 26, where m the total mass of the system holds. We have obtained the conditions 9 and 11 again. That was solution by second way. Third method. Let us consider again the point P1 with the mass m1 and the forces F21 and F31 given by the formulae 3 and 4. It follows from the text of the problem that the total moment with respect to any fixed point or with respect to the mass center of the forces acting on the point P1 must be equal to 0. Thus, we have expression 27, where the symbol cross denotes the vector product. Therefore we have expression 28. But because cross-product vector are 1 by itself equals 0, formula 29. From 28 we have 30. Using the formula 8, the last relation can be written as follows: next three equations. The vectors are 1 and R3 are non-collinear, and different from 0. Therefore we have their cross product is not 0. It means A12 equal A13. And similarly A12 equal A23. And we have rederived the condition 11. Taking into account that all the distances a, I, j have the same value a, from the equation 7, concerning the point P1, using the relation 2, we obtain next three expressions. This is the condition 9. The same condition is gotten result of similar calculations for the points P2 and P3. The method described here does not differ essentially from the first method. In fact, they are slight modifications of each other. However, it is interesting to notice how application of a proper mathematical language, that is the cross product, simplifies the calculations. That was solution by third way.